Well, first of all, welcome. This is Guido Caldarelli from University of Venice, and he's been doing a ton of stuff in understanding world and physical social phenomena in the context of using networks and graph theory as the fundamental tool. So welcome, Guido.
Thank you very much. So I will just present a few basic concepts on that. Probably will be boring for somebody that is expert in the field, and probably will be incomprehensible for others. So I will try to stay in between, so somebody will get some idea back out of this talk. And at the end, just at the very end, I will just present one of the applications on which I work the most, that is in financial networks. So the things I would like to talk you about relate to complexity. Complexity is a difficult to define field in some sense, because there are various definitions, and all of them lack some basic and important property. But essentially, all of those also agree on one point, that you have a complex behavior when you're considering a lot of elements in your system, and those elements interact with each other. So this comes from the seminal paper in 1972 by Phil Anderson. So more is different. And the idea is that, okay, if you have a brain, a neuron is a cell, those very complicated and complex things, but probably doesn't think. But if you put all the neurons together, then you have a brain and these things. So you have the emergence of new phenomena. And also Stephen Hawking was suggesting to embrace complexity. This should be in his view, the century of complexity, because somehow most of basic physics is not known. There is a lot to discover yet, and but I mean, we have some idea. In this field, we don't have any idea, and essentially, it's like when you start how to build bricks, but you don't know architecture, how you put those bricks together. So the idea that many colleagues have on that field is to, take some lessons from critical phenomena, that is a traditional part in statistical physics, where you study scaling relations, when you have a power law divergence of many quantities. You have a universality. So, for example, if you study magnetic susceptibility in phase transition, ferromagnetic phase transition, it doesn't really depend on the substance you're studying. So the behavior is the same for everyone, because it has to do with very basic physics. This scale invariance means also fractal behavior is another way to say that. And many of the things that we are used to doesn't work any longer. So let me be fast on that. What is the complexity I'm interested in? Is the complexity of the world around, because these are very old data, but I mean, still impressive. So this is 2020, more or less, the data deluge. So we have a huge number of bytes that are produced every day. So you have these on the poster on the right. You may see how many Zoom meeting we have. This is a Meet, but I mean, it's the same order of magnitude, probably more. But every minute of the day, how many books are read, how many movies are watched on Netflix, how many Amazon packs arrive. That is impressive number. So essentially, every year we double or more all the knowledge or the data we already had. So one idea of statistical physics is that these three guys told us how to do, is that when you have so many interacting particles, well, you can use some framework, theoretical framework, and then by using Maxwell-Boltzmann distribution, by using ensemble ideas by Gibbs, by using all these properties, well, you can describe what happens when you have a bottle of water, atom by atom. You can link the microscopic world to the macroscopic one. But why? Because you have very specific behavior in these systems. So all the particles can be described by an average. And for example, if you consider their velocity, they're more or less around their mean value. And then you can do computation out of that. You have approximation, those approximation work. If you would like to apply these ideas to the society, well, the situation is pretty different because we are not particles. People are not particles. You can't describe them by using just two parameters, position and velocity. And furthermore, everywhere, whenever you're studying social systems, you don't have Maxwell-Boltzmann, you don't have Gaussian phenomena. Well, you have some, but essentially you have fat tail phenomena. And so, make approximation with this distribution is by far much more complicated. And I mean, we lack these geniuses. I mean, whereas we need another Maxwell, we need another Boltzmann, another Gibbs. So we are trying to follow this path. But one of the modern approach to that is to start describing, at least mesoscopically, if not microscopically, which is the geometry of the interaction. And so in some sense, this is a paper I was involved with some years ago. You would like to write down a physics of humans, a physics of the society, with all these problems that I just listed. So let's try to, describe what's going on. It's a sort of Asimov foundation idea, that on average, you can describe which is the behavior of population, which is the behavior of people. Even if the foundation, things don't go smooth. So the individuality of people plays a role. So the technical part which we challenge complexity and complex systems is that of graph theory of networks. And this is very useful and also very general, because if we define a complex system by means of a system in which you have many elements and those elements interact, it seems natural, at least to me after all these years, to consider elements as vertices of a graph and any kind of interaction as an edge between these two vertices. And if you consider collaboration of people in a movie, in a paper, or whatever, if you consider exchanging emails, if you consider all these kind of phenomena, the interaction is very simple, it's reciprocal, it's symmetric. We are chatting each other, we are collaborating together at the same paper, the same movie, whatever. You can decorate this interaction and say, for example, no, it was me calling you at the telephone. It was me looking at your web page. So you may have directed interaction, then you put arrows on the edge. You may have weighted interaction, then you put weights. You may have a lot of other refinement to these basic ideas, but essentially this is still a network. And the property of these networks are remarkably universal. And this is the first key message of this talk. And which are these properties of the networks that are remarkably universal everywhere? So in many cases, believe me, almost any case you may imagine, you have a very explicit and clear scale invariance. So fluctuations are pretty large. So fat tail distribution in any statistical quantities of interest. They are a small world structures, so you can navigate them very fast with a few steps. They are also not smooth in another sense. They are very clusterized. You have cluster of things, and the communities are called in the jargon of networks. And all these together form other distribution, the distribution of centralities, who is the most important in my system, that again are not smooth, are not Gaussian, so are very particular properties. So one of the things that much more, but I mean in 20 minutes I would like to be as fast as possible. Scale invariance, if you consider ourselves, and I mean I don't see you now, but I'm pretty sure that there is an average height. Everybody's tall, more or less the same. There would be somebody taller, somebody shorter. And if you plot, which is the frequency with which this happens in any society, in a classroom, in your office, wherever, okay, then you have an average value. This average value is also very popular, so fluctuations are small around that. You may have people that is 20% taller, 20% shorter, but that's at most. This is not what happens in any society. I mean, if you consider how many followers you have on your social, how many followers, a sport hero, an actor, an actress have on their social, well, this can be thousands easily, hundreds of thousands more than you. These are several orders of magnitude. If we bring back this behavior to the typical comparison we do where we see each other, how tall are you, or which is your height, this kind of question. It's like having somebody that is 2 millimeters tall or, 300 meters. That would be pretty strange, So in some sense, we are not used to these differences, but in networks, they're everywhere. And on X or Twitter, whatever, I mean, this is a technical paper in which we analyze that point that has been questioned in the past, but this is a real scale invariance. If you see cutoff, it's because the system you are considering is limited. So in some sense, you may expect. Small world is a property that we learned from the activity of a sociologist. That was an American sociologist, Stanley Milgram. This is a paper of 1967. And he was interested in studying the structure of society in US. And then it took, I don't know, probably all of you are very young, so I don't know if you know about this very large book, the telephone list of places. No? So it took random people living in Omaha, in Nebraska. He was living in Boston. I was asking them if they knew a target person. If they knew, the game is over. If not, they should pass, he sent an envelope, a letter to those persons, should pass this envelope to somebody else who, in their view, could be in close contact with this guy, could be an acquaintance of this guy, okay? So he didn't expect, well, I don't know what he did expect, but probably he just wanted to study the structure of society there. But at the end, out of 100 people, almost one half answered and connected with that guy. This is a real chain, starting from people working in a shop, and then a series of intermediate people is connected with the guy that was a stock dealer in a bank in Boston. Okay, so if you plot the frequency of the length of these chains, then on average, the largest and most probable value is 6. So this is the 6th degree of separation. That was in the US of 1960s. And actually now, I mean, it's, much shorter, the distance. So some people analyze which is the society within Facebook, that is a large country, because it's, at the time was, I believe, 700 millions, so larger than Indonesia, for example, people in this social. And this distribution is not fat-tailed, as a distinct behavior. And the mean is 3 point something, but the mode, so the most probable value is even shorter. So by far, less than 4 steps are enough to travel the system, to be connected with everyone else. And this is probably something we should remember about social. So you are exposed distantly to everybody. So there is no inner circle in social. Another important part in networks that can explain some of the properties we see in complex systems is the clustering, so the formation of different communities. And this came all out of the same basic mechanism. So you take a bipartite graph, this is technically what it is, this object there, and imagine that the yellow circle are people, and the green squares are things they do together. So 1, 2, and 3 can write a paper together, paper A, and 2 and 5 wrote another paper, paper B, and so on and so forth. And then you connect people, one with each other, if they wrote the same paper, all the 3 of us. So 1, 2, and 3 are connected, and 2 is also connected with 5. And you can also create a taxonomy. So if papers have been written by the same people, well, they probably are similar. Okay, so you can clusterize people, you can clusterize things. Any network coming out from social systems is formed with the basic mechanism of defining the proper bipartite graph. And this forms communities. This is one part of the story. The other part of the story are the centralities. Who is most important in a network? Well, this depends strictly on the question you are interested in. If this is the same network, I took the picture from Wikipedia, so it's very. They added the few examples now, so it's much larger now. This image, but essentially this is the same graph, same vertices, same edges, and the heat map is related to the centrality. So you may ask, which is the guy who has most of the connections? And this is the first case, top left, and this is a degree centrality. Then you may define, okay, but if you want to travel across the graph and visit every other vertices, which are the vertices that are nearer somehow to the others? This is like living in the center of a city. If you live in the center of the city, you can travel fast to any other zone. If you live in one of peripheral eastern part, well, you take a lot of time to cross the center and arrive to the west. Okay, so this is centrality is geographical, if you want. Centrality is a closeness centrality. You can also say, well, look, that's not important. I would like to know what the people who are bridging communities. And if, for example, I work in Venice. Venice is on the water, as an upper part, a lower part, and those two parts are connected by 4 bridges. If you destroy those 4 bridges, you just have to take a boat, not to go from one side to the other one. So this bridging centrality is important for certain questions. This is the betweenness centrality, and again, here is same graph is very different. You can, describe the graph as a matrix, an adjacency matrix, and study the eigenvector centrality, and this is again another one. So this centrality stuff has really to do with the question you are asking. But the point is that once you have the centralities, once you have this bipartite way to build the networks, well, you can cluster efficiently any system into communities. You can do coarse graining, you can do renormalization group if you want on that. So on the left, there is a typical example we all use, is a karate club. On the right, there is a much larger structure. This is a network of emails that have been exchanged in a European university in Spain, Tarragona, in Spain. And you can cluster all these emails, and they turned out to form different clusters that are being colored here in this picture. And those clusters correspond to the departments of the university. So all the people in the department write to each other, seldom writes somebody else, and in yellow you have central administration that is, connecting with everybody. So these are the properties of networks and are pretty universal. How you can apply to society? Well, people, for example, start to study past history, and I don't know how many of you are familiar with that, but this is a typical example in sociometry. These are families, those names are Italian surnames, are families that were powerful in the Renaissance in Florence, in Italy. And the Medici, you probably heard about that. And one line between 2 families is a marriage that has been engineered by the 2 families to create an alliance between them, okay? So forget about Romeo and Juliet, that's politics, it's not to do with love. But these are the alliances in these systems. And then you can easily spot that the hub, Medici, turned out at the end to be the most powerful family in that place. And of course, they have to fight with that. And fighters, the strongest fighters they have are people who are in the periphery in this picture. So Pazzi, at a certain point during the Renaissance, people of this family of Pazzi, tried to kill the Medici. There was a coup d'etat in Florence and with people killing each other at the time. But this is in the past, but also in the present. If you take these two guys, probably their relationship is not very well. They're on social. If you study a social now, which are the contacts, well, it's more or less the same shape. So you have one vertex with a lot of connections and others we have much less. This is a real network, is the 1 day, 1 hour contacts on a mobile telephone company in Hungary. And so this is real phone calls between people. So you see that a lot of people doing few calls and few doing a lot of calls. This can be used to track what people does. It's also used to track what people share about opinions and ideas. And there is a whole part of activities that is devoted to disinformation, fake news, or whatever. This is a number that came out a few years ago about how lies spread in the community. Of course, as in many things, the US was starting using social as a way in which you get informed. And now what was true a few years ago in US is true everywhere in the world now. And so if 50% of Americans in 2016 used the online platform as the primary source of news, in Europe is exactly the same even now, and everywhere is the same even now. So propagated from Americas to the rest of the world, and essentially these platforms are important because most of the news we take from them. Okay. So what's going on? Well, there are people in France. This is David Chavalaria, is running a website. It's called the Politoscope. And he was tracking down the retweets of people, retweets based on declaration of politicians. Okay. And so essentially by just counting how many retweets, how many comments, how many interactions, it depends on the maps, this is one of the many they produce, how many interactions you have with a certain given candidate, in some sense this is telling to the world, to you, if you don't realize that, which side of the political competition you are. So they made this spectroscopy, and the names here are names of French politicians. So starting from the left, this Mélenchon was in the Socialist Party, then you move to the center, and then you move to the right, to Marine Le Pen. And you can see, essentially, you can measure how much you agree with one party or another one. So this is a map of the people discussing there, and it's a map also of their political ideas. So this is a sort of a joke I always present. This is the country of Descartes, so very rational. I'm from Italy, as you can witness from my accent. We are more Renaissance men, so a little bit more mess you can have in our country. This is an analysis we did that's everything more mixed. So the distinction between left wing and right wing is much more smooth. So the spectroscopy here works less satisfying than in the French case, but this is probably has to do with us, not with the method. So let's go to the financial network. Please.
Let me understand that thing. That's actually a fantastic example of what graphs are for. So you have a situation where you have one country where you have a nicely structured, linearly structured political spectrum.
This one, yeah.
Here yeah, France and US will probably be the same. I'm not sure about other countries. Whereas Italy, you have a much more tightly connected spectrum. So what does that mean for things like stability of the social dynamics? Because you're imaging social dynamics and power struggles and so on. Does that have an implication for stability of the country or how such structures evolve?
Well, a caveat first. I'm just a poor physicist, but I listen to many sociologists talk about that. The real danger in that, I mean, these are photographs. I mean, this is a picture of the society. The real danger you may spot here is when the situation polarizes. So people who are not of the same color here don't talk any longer with each other. Okay. So there is one guy, there is Filippo Manxer, is in Indiana University, and he realized many movies about that. I didn't put a movie because it's tricky on PowerPoint, but he shows the dynamics. This is what you're asking about a community on a social, and very sadly, you see that as the things proceed, edges disappear. So at certain point, they become disconnected. Okay, so in some sense, you may think that having such a very linear, with a few overlap structure could be more fragile than the mess which we are here in Italy. And this picture, by the way, makes sense. I don't want you to become expert of Italian politics, but the fact that you have here Silvio Berlusconi, that was powerful guy in charge of as a prime minister of the country, very nearby to one that is nominally of the left, like Matteo Renzi, makes a lot of sense, because they are both in the center, actually, not on. It's not very polarized. It started to become more polarized even in Italy. I have the idea and impression that it's going to be more polarized everywhere. But as long as we have ties with each other, even if weak ties, those guys, and it makes sense to me, say the situation is not that bad for social dynamics. So it's important to keep, how to say, contact, okay, not to split in two, because this, when you start splitting in two, that's no good sign. Okay, so, I hope I answered to that.
Yes, that's interesting. And maybe one more. I guess, how does social dynamics reflect power dynamics? Because I can imagine tightly connected components like this in an authoritarian country where it's the people against the leadership. It's a bad country, but the people are connected, right? So when to separate out what can you tell about a country from such graphs? Because it's not like a clean mapping, it seems.
Mm-hmm. Well, I mean, for example, the presence of inner poles, if this image is can be used. So the fact that it's not just the red on the left and the brown on the right, but there are large position in between, seems to be how to say, from one side a recipe for some kind of stability, because there are intermediate positions somehow that can mediate the two opposite poles. On the other hand, this is not good for stability. I mean, in Italy, we have several parties, and that didn't really work well. I mean, it's pros and cons in the two things. Probably if you have just two parties, situation is sharper. You can have this problem of polarization and splitting into two, but somehow you can. It's easier somehow to take decisions. Okay, and I can't sell one model against the other, because I mean there are really pros and cons in the two things. This seems to be very more robust than one object that is split in two. Even this seems robust somehow, because positions are not so very different from the two poles, and also there's a lot of people in between. What is scaring to me is that I didn't put, but there is a whole series of studies on that. If you study, okay, this is politics, it's just plain and simple politics. What do you want to do with economics? What do you want to do in the future, immigration, the key concepts? The same structure and same polarization is also in the debate on vaccinations, on diseases. Okay, so things that we believed belonged to science are heavily affected by your political views. This came when I first saw that, came unexpected. Now I got used to that. Probably everybody got used to that. But that's another way in which you can measure quantitatively those phenomena that are pretty new, I would say.
Yeah, makes a lot of sense. Thank you.
Thank you. Thank you for the question. So the more boring part, financial networks, I hope to make less boring. And okay, there's a series of papers we published on that. The key quantity stems out from, that I would like to talk about, is called DebtRank, is used in central banks, came out from purely theoretical analysis made on graph theory, and turned out to be useful. So this is a good example, a success story, my success story in this field and complexity. This plot you see there, green and yellow vertices, is a representation of Italian stock exchange some years ago. Green are companies, and red are people. And you can trade people in Italy, even now, not in the past. And this is an ownership network. So who owns whom? And one company can be owned by another company, so a link between two green vertices, or can be owned by individual people, and this is the red vertices. And these are, of course, the largest shareholders in the companies. So this is a picture of companies in the stock exchange. This is, again, you see the hubs and the periphery. So few things have a lot of connections. So few companies have a lot of ownership in the others, and other are just owned by these guys. You have communities. We don't enter into the detail of that, but it's essentially the four properties I showed you before. And this is holds in Italy, also in US, everywhere. I mean, all the stock markets are more or less similar. Point is, some of these companies are banks and or other companies, and banks have ties that originated from the balance sheets, and so assets and liabilities. So to pass to the technical side, you can take one vertex there and just explode the quark, the protons, the neutrons in which this atom is composed, so the subatomic particles. And every company has this structure in which you have assets. You know what assets is. So you have liabilities, so things you have in blue, things you don't have, or debts that you have, liabilities, and the difference must be positive, otherwise you're bankrupt. So equities in this representation are the green part. Is fairly more complicated than that, but I mean, this is a model that works. So yeah, things you have blue, things you have to give to somebody else red. The difference must be larger than zero, and these are the equities. So imagine this is a company. Any day, every day there is a problem, there is a trouble. So at certain point, for example, happened in 2008, mortgages, households go down in their value. So what happens? That on the asset sides you have a reduction. So mortgages in the deposit of your bank, this company is a bank, are worth instantly less. So you have to re-equilibrate things, because the green part is the difference between the blue and the red, and this means that also your equities are reduced. Or if you want, you have enough money to pay back your debitors, you have less at the end. And so this is what happened to your company after a shock, an exogenous shock, something that happened outside your company. This is reflected in how the values in your company are changed. Less value for your investment, less equity. But this is, okay, a situation of just distress. It can be much worse than that. If you have a big shock, well, all this value goes to zero. Then all your equities, you pay back debitors, but you still have more debts than assets, and then you're bankrupt. So what happens when you're bankrupt? And this is a problem that relates what is called the interbank network, that most of these debts you have with other banks. You don't pay back those debts, they go in distress. Eventually they could go bankrupt, and so on and so forth. So you have an avalanche of bankruptcies. So how to study this? How to assess quantitatively what's going on? Okay, so I need just another concept, the concept of leverage. You probably know what I'm talking about, but in this simple model, A are the assets, L are the liabilities, E are the equities. So AIJ is the asset of type J owned by I. LIJ is how much money I must give back to J. EI is, the difference of these two that must be larger than zero. We define leverage the ratio between assets and equities, and is leverage in a physical sense. So you can do more things than your strength with the leverage, like the guy in the picture. So with an example, that will be much easier to get. I would like to buy a house. This house is worth $200,000. Okay, but I just have $40,000. So I borrow from the bank 160 as a mortgage. Okay, so 160, 40, and then 200. So at the end, I would like to use this definition of leverage. Now I got a house. This house is worth 200,000. So this 200,000 is my asset. The equities, the money I had before, is 40,000. So if I take the ratio, the leverage is 5. What this 5 means? Okay, is a quantity that related to risk amplifies my possibility to do things. Okay, so I couldn't buy the house with my money. I borrowed them and then I bought. Now imagine that there is a fluctuation in the market. I didn't move in, and the houses overnight are $220,000 worth. And then I say, well, you know what? I will sell immediately back. I will sell. I didn't move in. And then I give back the money to the bank. For simplicity, let's assume there's no interest rate. So I was starting with 40, and now I have 60. So the market went up by 10%, but I gained 50%. I got 60,000. I used to have 40,000. Okay, so I took 50% of my capital more. So this is the leverage. It's a leverage of 5. I multiplied by 5 what was the fluctuation in the market. I was able to do that with the money that I took from the bank. Okay, so what is the idea of DebtRank? This is a quantity we introduced and used. Imagine that you have an interbank network. I and J are banks, and there is a shock, an exogenous shock, and so J loses part of the equity. Now what happens? I also, that was investing, okay, let's go back. So this is the original situation, shock on J, so the equities are reduced. And also the value of the investment in I must be reduced. Because if I say to bank K, okay, I borrowed, I lent $1 million to J with 2% of interest. Why don't you buy my contract? Give me just $1 million and then he will give the interest to you. Well, K will not accept because now J is in distress and there is a probability that he will never pay back. Okay, so while the face value of the contract remains the same, the market value of the contract is strongly, in some case, reduced. So it can be garbage at the end. So even the value of the asset is reduced, and then also the value of the equity of I must be reduced. So again, you see, look on the right. On the left is reduced the asset, and then it's reduced the asset of I and also the equity of I. So this is the way in which distress propagates, and this is essentially a network measurement. So external shock implies the devaluation of my asset. If J is struck by a shock, well, it's also a problem for myself because J will not pay back the debt. Okay, so we introduced this quantity, the total loss of equities that there is in a system because of an external shock, and this is computed essentially by looking who's connected with whom. That's the idea. And the microscopic rule that is in the DebtRank, I'll tell you for those of you who are interested, is computed in such a way by taking this ratio. So the ratio at 2 time steps of my assets is equal to the ratio of the equities at 2 time steps of the borrower. So if the equities of the guy are reduced in time because of a shock, at the next 2 time step, even my equity that I invested in him is reduced by the same ratio. 10% there, 10% my asset. Okay. Sometimes this is good, sometimes this is very sharp. It's a bit like in Taylor expansion, no? So this is at least the first quantity you may attach to this phenomenon. Okay, you do an equation that writes down which is the relative loss of equity in time, and this system works because it allows to compute which is the effect of a shock on a system in such a way that you don't have to do, too big to fail procedure that is very problematic for a variety of reasons. So, for example, here is a plot of DebtRank in which the impact, that is this point here, probably you can see, this is the largest impact on the market measured by this DebtRank, so everybody could lose 13%, but this is not a big bank. I mean, on the right, you have the large banks. So even a medium bank can create a disaster, and the point is you have to study which are the connections, not the value of the size of the bank that they are involved. Of course, play a role, but I mean, it's not essentially the same. We're very proud of that because these quantity, this is a slide from European Central Bank, and now it's used in Bank of England, European Central Bank, I suspect Bank of America, Bank of Mexico is used everywhere, and this is one way in which you do stress tests in banks. Okay, I probably sorry.
This family of analysis. So you have this like you model the leverage relationships, and you have this simple model of propagation of failure or bankruptcy via these relationships. So how complex would the dynamics need to be to make it fully accurate? Is it a matter of for practical application, is this simple model of propagation, like leverage propagation, sufficient? Do you have to capture more panic behaviors or time dependence, anything like that?
The panic behavior, no, it's not. Thanks for the question. Very, very precise. And we take into account more than the previous models. That is a chain, a cascade of bankruptcies that wasn't working because, for example, if you don't go bankrupt, but you have just infinitesimal equities, you're still okay. And then you're overestimating the health of the system, while in principle you are almost bankrupt. So the distress is large. But as long as you're tiny above zero, well, you're okay, and that's not good. So this is the basics of 2008 problems. We don't put the panic, the third wave of selling because of the panic, because this has to do with something that is not related to the figures that you have on you. It has to do with human behavior. So this is difficult to model. But the fact that you can take into account the propagation of distress to the network is already good. So if I can go on that pictures, and I hope to answer then to the question. We took the data before the crisis of 2008. We took all the models, okay? And we made some plots. And for example, we consider on x-axis here, there are the days, the commercial days around the crisis. This is the year of the crisis, 2008. And if you consider, for example, the typical standard stress test, okay, let's do a shock on mortgages. How many are bankrupts? How many are safe? This was the standard before. You don't have any precursor of the crisis. And all the crisis appears at the same moment for all the banks. If you study a more network-oriented quantity, that is, for example, the centrality computed with eigenvector centrality, that's good because it splits the risk between the different banks of different risks, but you don't have precursors, and okay, you have the crisis when there is the crisis. If you use DebtRank, that by the way accounts for 100% of the previous effects, well, you see that the distress is increasing in time, and then you arrive at the moment of the crisis in 2008, then it goes down and still oscillates. So it's good in this sense because it has precursors and aftershocks. The other effect, the third round, no, we are not able to model on that.
Well, actually, let's now expanding upon this, because there's two dimensions to expand this. The dynamics can be more sophisticated to capture, time dependent.
Absolutely.
The other one is more edges. I'm imagining trade networks. If you're investing in a company and its stock drops, then your leverage of that investment drops, which causes some lenders to panic, and stop lending to that entire sector, perhaps, or some other sector, and it propagates through regular economy, like companies, and also trade networks, which is yet another graph. So
you are absolutely right. And yeah. No, I mean, I thank you because you are introducing the next slides.
Brilliant.
And yeah, I mean, and in principle, we would like to do that. We would like to create a multi-layer network of economics. The point and problem is that nobody, not even central banks, that's bad news, have total knowledge and information about those graphs. So they are impossible to build. We worked closely with Bank of England. We couldn't have access to the data. We couldn't even know the guy who knew the data about the banks. So we wrote the software and they played the software we wrote on their data. But they told us that everywhere is the same. England, Italy, France, US. The central organization knows everything about the balance of their banks and their company. They know a bit about how much they are exposed to people overseas, so other companies abroad or other banks abroad. For example, in Bank of England, they knew which is the total exposure, the total debts against Italian banks or German banks. They don't know absolutely anything about the connection between German banks and Italian banks. But the market is the same. No, and so you're ignoring a large part of your graph. You just have the spot on your place. And in trade, this is much worse than interbank networks, because of course the trade is everywhere. So how to do? We've been challenged by those guys. Can you do the DebtRank? This was the question. If we don't know anything about Italy and Germany, and we just know something about England and Italy and England and Germany, and we don't know the singular edges, but we know on average the total amount of exposure, and we say, well, we can try. So we went back to statistical physics, and we created various graphs, ensemble of graphs. And to cut this story short, I mean, we used a very old approach that is called exponential random graph. And the idea is that you take all the possible graphs, G. P of G is the probability that you end up with that particular G. You don't know anything about this P. You would like to have an idea what it's about. And you are totally ignorant on that, and so you maximize the entropy. You define the entropy of the system in the usual way, Shannon entropy, and you define, now you have this quantity that depends on P, is minus P logarithm of P, of course, summed all over the banks. And then you maximize the entropy of your system, hoping to find the right expression for P. But you know something. For example, you know that whatever is this probability to find a certain graph G, this probability must be normalized. So you have a first constraint, that is this constraint here. Then you might or might not have other constraints. So you may know which is the total exposure. You may know which is the total weight. You may have other constraints. Well, okay, if you do the mathematics very simple of that, so you do the derivative of this functional L of P, well, you end up with this expression, e to the minus 1 minus lambda 0, that is the parameter of this constraint, minus the sum of these parameters here. So imagine that you don't know anything about that, apart that the probability is normalized. So this second part you don't have, and you have just this part here. So P of G is equal to this quantity, but this is a constant. So if you don't know anything about your system, Well, very likely the probability to find a certain graph will be the same for every graph. And this is the random graph model, so every graph is just the same. But as soon as you have any other quantity that could be of interest and could be a constraint that tells you something about your structure, well, you can, how to say, reduce the uncertainty, and you can find which is the P of G. We've been able to find which is the DebtRank in the global interbank network, so it went pretty good with Bank of England. We are very far to have a similar formulation for all the other networks you were mentioning before. So the trade network, the ownership network, commodities networks, financial services are all interconnected, of course. But this could be an example on how to proceed. So I will skip to the conclusion. These are the papers where we show what we did for this interbank network and determination with approximation of the analytical form of this distribution for the graphs, and that's it. I would just just skip to the conclusions. Apart what you can find here, written here, complex systems, there is a large amount of work to be done yet. Many of the things we are doing are partly understood, that certainly we lack on a strong analytical basis of that. But they allow us to have a different look to the problems and to be able to use the framework that we established for much simpler systems like thermodynamics. So thank you for your interest.
Yeah, thank you very much. So let me ask you one more question about the inference. So one nice thing about international, so I'm thinking, oh, let's do Twitter, what's called meme stocks. There you can watch people like on Reddit and Twitter talking about things, and rumors or opinions propagating through the network, ultimately, affecting actual stock values. And you don't have to actually know it all. You can just infer the various noise in various channels to find a correlation to final stock prices to figure out presumably the causal structure. I guess my question is, I can say this in theory, is that actually doable? Do we have enough information to infer the causal structure from the available data?
I don't think so, for a variety of reasons, because the data is messy, because we have bots in Twitter, we have disinformation on Twitter, people writing false things, whatever false means, whatever true means, by purpose. There is a whole spectrum of what false and true is. You may believe in what you're writing, you may not believe in what you're writing. It may be as true as somebody else's vision, and so legitimate, maybe not. I mean, it's not easy to assess these things, and this create one noise in the signal that is almost impressive. And then no system is totally isolated, because, I mean, of course, ideas can propagate on socials, but ideas propagate also in the old way. So you meet people in the street, you just discuss with them. So it's impossible to have all the parameters together, such that you can do a formally clean causal inference, okay? But you can spot some signals. This is clear that you have signals. That's
maybe let me simplify it. If propagation of price shocks, I can see that somebody is dumping something, a commodity, nickel, and then later on some other companies, apparently unrelated, its stock goes down. I can start correlating these signals, but I'm not sure how noisy that is.
No, this can be done. This I believe can be done. Yeah. No, this you can do. Yeah. No, I thought I was thinking, I don't know why, about politics. But
which
no, yeah.
Yes. And actually, so maybe just as a final one to understand the scale of this thing, I'm thinking relating it to the closest physics problem I can think of in terms of complexity and non-local multi-scale behavior. I'm thinking like magnetohydrodynamics, where you have several laws that are all messing with each other, but locally they're simple, but they propagate via a semi-homogeneous, semi-heterogeneous kind of causal graph, because you can, right. So I guess, can we get an idea of kind of the complexity of that system or similar physics system to the logical social system?
Well, in the example you're making, we have a fairly good knowledge of what's going on, and we have been able through the years to mathematize the various behaviors. So we end up with the questions that are coupled. We don't know how to solve them, and add to that the precision in measurement is, preponderant effect, because any change in the initial position of the things may propagate, and Lyapunov exponent can explode and have the chaos. Okay, in all the system we are describing, we are very far from a mathematical modelization of what's going on.
Yeah,
that's it's not a detail, and for certain things, certain point Twitter has been used because Twitter was more or less cheap or possible to download the data, and so people studied what was available. But there are a variety of other social interactions that are mediated by technology that lacks mathematical expression on that, and so again, we are at the very beginning of this story. That's
well,
no
fair.
question. Yeah.
Well, cool. Well, thank you very much. It was a fascinating talk.
Thank you.